In this video, we're going to study the behavior of the function h of x equals x to the fifth plus x minus 2 over x squared minus 1 around 1. Now, before we do that, we're going to just look at a few aspects here. First off, domain. Well, the denominator can't be 0, so x squared minus 1 cannot equal 0. If we solve that, x cannot equal plus or minus 1. So in interval notation, we have negative infinity to negative 1. We want to exclude negative 1. We also want to exclude positive 1 and union 1 to infinity. So there's the domain of this function. So 1 is going to be our point of interest, but it's clearly not in the domain. So let's investigate further using a limit. So the limit as x approaches 1 of our function, x to the fifth plus x minus 2 over x squared minus 1. Now the first way we should always try to solve a limit at a point is via direct substitution, which means basically plugging this 1 in. Now we know plugging 1 in will make a 0 in the denominator. That does not necessarily mean the limit does not exist. So let's plug it in and see what happens. So we have 1 to the fifth plus 1 minus 2 on top over 1 squared minus 1 on bottom, which we know is 0. The top, notice, is also going to calculate out to 0. This creates what we refer to as an indeterminate form. That means this form of the limit cannot be determined via direct substitution. We can't clearly say it's 0 because there's a 0 in the denominator. We also cannot clearly say it doesn't exist because there's a 0 in the numerator. There's going to be something more interesting going on. Now, since we're around the point 1, what we can do is we can use the linear approximations of the numerator and denominator to see further what's going on. So let's say we define the numerator to be x to the fifth plus x minus 2, and we define the denominator to be x squared minus 1 to be g of x. What we're going to do is find the tangent lines of each of these at x equals 1. And we've done that plenty, but let's just go through it. F prime of x equals 5x to the fourth plus 1. So f prime of 1 equals 6. We also need f of 1, which we calculated earlier right here. F of 1 is 0. So the tangent line, we'll call it L sub f of x, is the slope, which is 6, times x minus the x value plus the y, which is 0, which simplifies to 6x minus 6. Now, we're going to do the same thing with g. G prime of x equals 2x. G prime of 1 equals 2. G of 1, we also know, equals 0. We actually calculated that earlier. This is an important part of the indeterminate form going forward. So, as we build our tangent line, we'll call this L sub g of x. We know that the slope is 2 times x minus the x value plus the y value, which is 0, or simplified, 2x minus 2. Now what we're going to do is we know that h of x can be approximated by these tangent approximations, L sub f over L sub g near x equals 1, because the tangent lines are good approximations locally around 1. Well, remember what we're doing. We're looking for the behavior of this function around 1. So what we're going to do is actually take the limit of their tangent lines instead of the original function and see if we can find out some more information. So we're going to take the limit as x goes to 0 of 6x minus 6 over 2x minus 2 as x goes to 1, Now, what you'll notice, if I plug in 1, I still get a 0 over 0 case, so this is still an indeterminate form. But think about what we learned about limits earlier, is I can do some factoring. So I have the limit as x goes to 1, and I can factor a 6 out of the numerator times x minus 1, a 2 out of the denominator times x minus 1, and those cancel. So I have the limit as x approaches 1 of 6 over 2, or 3. So according to what we're finding, this is telling us the limit should exist, and it should be 3, using our tangent line approximations. Let's verify this graphically and numerically. So I've already got my function entered. And if I look at the graph, notice the smooth behavior at 1. Now it may be hard to see exactly where that is hitting. If we zoom in once, and we're going to need to move up just a little bit. Let's move that window up because we said it would be 3. Let's move that y max up to 5. So here's x equals 1. And if I trace up, it looks like it's nice and continuous there at 3. Now, if I try to calculate the value at 1, it doesn't exist. That does not surprise us. But we know that the limit is going to exist there because of that nice smooth behavior. It's going to the same place from the left and the right. If we wanted to verify this numerically, we can go to our table, and we want to get closer and closer to 3. So 3.1, 3.01, 1.1, closer and closer to 1. 1.01, 1.0001. Again, if we put in 1, we get an error. 0.9999. And that's not going to be exactly 3. If I go on it, there's the decimal points that the calculator can't show. But what we see is, as we come in from the right and from the left, both sides are approaching 3, verifying that the limit. So as we conclude, the limit as x goes to 1 of our original function, x to the 5th, plus x minus 2 over x squared minus 1, is going to be 3.